take a look at this check on enthalpy and calorimetry. So in the first question, it says to describe and diagram the transfer of energy for endothermic and exothermic processes using calorimetry. And so here I have an example of each process. On the left there's exothermic and on the right there's endothermic. And so just remember the signs of enthalpy or heat for those. So it's a negative sign for exothermic and a positive for endothermic. And so basically what we do is we put these into our cups, our insulated cups, and then we measure the temperature of the water before and after the process. A lot of times we have a stir rod that goes into there as well, and we want to know what happens. Well, on the exothermic one, we end up finding that the H2O gets warmer. And so that results in a change of temperature for the H2O that is going to be a higher final temperature than the initial temperature. And so this feels warm to us if we were to put our hand in it or if we were to hold it in something that maybe wasn't as insulated. And if we're looking at what happens to what's going on with the system is releasing that heat. And so the positive value that you will get for Q for the water, okay, because the water is absorbing that heat, is going to be equivalent to the same value. The magnitude is going to be the same, but in opposite directions. So the negative Q of the reaction or the process, okay, if it's a physical process that's happening. On the other side, for an endothermic, it's exactly the opposite of that. So the H2O gets cooler. The change in temperature for the water is going to be where the T initial is actually larger than the T final. And so we know that the heat is moving from the water itself into the system or the reaction, whatever reaction or process is occurring. And so the negative Q, it'll be a negative Q for H2O when we do our calculation, is equivalent to the amount given off from the system to the surroundings of the process or reaction. See if I can get my N to look like an N here. There we go, a little bit. So we can do some calculations with some data from this. So here is the second question. What is the heat of a reaction if the initial temperature of 100 milliliters of water in a calorimeter is 25 degrees Celsius and changes to 38 degrees Celsius when mixed in a calorimeter? So we have some sort of reaction that's taking place. A lot of times it's taking place in aqueous solution, and one thing that I notice is students think that that is the system, but actually the water itself is the surroundings, and whatever the reaction in aqueous solution that's occurring there is the system, and so it doesn't look distinctly different. So again, we're going to use our Q equals Cm delta T. And we know that the C for water is 4.184 joules per gram degree Celsius. And that's why calorimetry works really, really nice, because we always know that for water, even if we don't know what the specific heat is for something else. And so again, we want to know what the heat of our reaction is going to be, which is Q. We know what everything else is, and so we can go ahead and determine these. Now, when we do this, it's interesting that 100 milliliters of water is used instead of a mass, and we know that we need mass, so how do we get that? Well, we know that the density of water is 1 gram per milliliter, and so we know that 100 milliliters is equal to 100 grams. So we can use that. All right, and we just want to plug in our values. So Q is going to be equal to 4.184 joules per gram degree Celsius times 100 grams times the change in temperature. And so it started at 25 and went to 38. So 38 is our final. So it'll be 38 minus 25 degrees Celsius. So we're just going to go ahead and do our calculation. Now, it's important to note that this is the Q for the actual water because we're using specific heat of water. Okay, so this is for water. All right, so let's go ahead and do 38 minus 25 first. It's 13, and so then we're going to multiply that by 100 and also times 4.184. And we get a value of 5,439.2. With sig figs, we should have 2 sig figs, so that's going to be 5,400, and our units that are left over. So let's take a look at how units cancel. Grams cancel, degrees Celsius cancels. I'm left with joules, and so that's going to be in joules. Okay, so we already said that the Q of the water is equal to the negative Q of the reaction or process, which means the Q of the reaction is equal to negative 5,400 joules. And that is our actual answer. Okay. Since it's a negative Q, we also know that this particular reaction, because it's negative, okay, negative Q is exothermic. So just a little analysis if you're asked for if it's endothermic or exothermic, which we weren't, but sometimes that's nice to think about anyways. All right, let's take a look at this last example. So again, it's going to ask us what is the heat of reaction. So we're looking for Q again. Okay. We have 354 grams of glucose. If the heat of combustion for glucose is 2,808. So in this case, we don't need to actually use Q equals Cm delta T. We are just going to do a conversion. So in this particular case, we are going to do a conversion because we already know what the Q is, or the heat is. So we're going to go from grams to moles, and then we're going to go from moles into kilojoules. And I will say for a lot of things, we do know what the heat of combustion is, and there's usually some sort of a table or chart that will give us those values. We also need to know molar mass. Okay. So if we want to know our molar mass, we haven't done this in a while, but I said it never goes away for us. So for C6H12O6, we've done this before. I'll do a really quick example. It's going to be 6 times 12 grams for carbon plus 12 times 1 gram for hydrogen plus 6 times 16 grams for oxygen, and that gives us a value of 180 grams per mole for our molar mass. Okay, so now let's put these all together. So we're going to start with our 345 grams of glucose. We know that we have 180 grams for every 1 mole. And we know for every 1 mole, there are negative 2,808 kilojoules. So 345 times negative 2808 divided by 180, and I get negative 5,382 with sig figs. We started with 3 sig figs there, so we're going to round to 3 sig figs. So it's going to be negative 5,380 kilojoules. And that is our answer. That is also exothermic because it's negative, and heats of combustion are always exothermic.